So hello, in this podcast we're going to talk about the pumping lemma. Why am I talking about the pumping lemma? That's because some of you were confused about how to apply the pumping lemma to prove that some languages are not regular, right? So I thought, okay, let's do a podcast and show how this works. Let's work out a couple exercises. So before that, I actually want to review just a minute what the pumping lemma is about, right? What's the pumping lemma? So let's do an example. So L is the language of strings starting in 0 and ending in 1. It's an infinite language, meaning that I can come up with as many strings I want. I mean, there's an infinite number of strings belonging to this language. I can always find more. I built a DFA recognizing this language. Okay, and what I want to do now is try some input and see what states are visited for each input and count them. Well, let's observe what happens. So let's try the string 0 1. It is in the language because it starts in 0 and ends with 1. Okay, first of all, we always visit the initial state because that's where we start from. So it's always visited. It's a given. So let's not count it. Let's not count this. So okay, we're in the initial state, we see a 0 here, and we visit this state here, right? Then we see a 1, and we visit this state here. So our string of length 2 made us visit these two states here. But what happens if I add more symbols? Now, if I add, let's say, another 0 1. So what will happen now is that I see the first 0, so I move here, I visit the first state. I see the second, the 1, and I visit this second state here. Now I see another 0, and I revisit this state here. And the 1, so I revisit this state here. So I visit these states twice. Okay, now that is inevitable. Why is that? Because we have more symbols than states here. So we have only 2 states here, but we have 4 symbols here. So by the pigeonhole principle, okay, because for every symbol I must visit another state, well, we can visit the same, but the point is that if I have to visit a state for each symbol, and I have only 2 states, and I have more than two symbols, then some states must be revisited. So you loop. You have to loop if you have more symbols than states, right? In this case, I'm looping because of this substring here, right? So until 0 1, everything was okay. I visited every state exactly once. Now, when I added this substring here, I revisited these 2 states there. What the pumping lemma is saying is that, well, first it's inevitable that if you have a string which is longer than the number of states in your DFA, you have to loop. That's inevitable by the pigeonhole principle. But what is also saying is that, well, if you loop once, you can loop twice. So I can add another 0 1 substring here. So what I have here, I have 0 1, so 0 1, then I loop 0 1, I looped once, why not twice? 0 and 1 again, and I still accept, I still get strings in the language. But if I loop twice, I can loop 3 times. So 0 1, I accept, 0 1, I looped once, 0 1, I looped twice, 0 1, I looped 3 times, and still I accept. This is an accept state, right? So I still get strings in the language. I can do this as many times as I want. I can pump, this is the expression, pump these strings as many times as I want and still get strings in the language. I could also just pump it 0 times and still get something in the language. So this is an example to actually give you a taste of what the pumping lemma actually is talking about. So what is the pumping lemma is saying is that if you have a language which is regular, so L is regular, then well, there must be a DFA recognizing it, right? Because it's regular. And this DFA must have a number of states. We don't know how many, but there must be a number, right? So we say this number is P. We don't bother building the DFA. We just need this fact to say that for every regular language, there's a P, a number P, which we call the pumping length, which can think about we can think about it as being the number of states in our DFA, right? Recognizing the language. So we have P, and now the fact is that if our language contains strings which are longer than P, so the length of the string is more than P, then that must mean that for the pigeon principle, I have a substring which can be pumped because my DFA is looping, okay, because I have too many symbols in this W here, okay, so that I have to revisit the same state more than once. But if I revisit, so if I loop, that means that I can take that loop and replicate it and replicate and replicate as many times I want. And that is equivalent to say in saying that W can be decomposed in 3 chunks, okay, and when I can pump this Y part as many times as I want. Well, now, just to make sure you understand, these things here are not symbols. They are just saying these are substrings. So each X, Y, and Z, each one of those are substrings. So they contain symbols. They're just a shorthand, right? So the important thing is that you know that there's a part you can pump in W. So this is what this expression is about. There's a part which can be pumped, okay? So maybe there's something before. This could be empty. So this X could be empty. This Z could be empty. But there is a part which can be pumped, which is Y, okay? So I'm actually leaving some things from the definition of pumping lemma out, but that's just to make sure you really understand, okay? You're free to actually go on the textbook and see the complete definition. You should be able to understand it after you understand the basic reasoning behind it. So we have a part in W which can be pumped. That means that X, Y, Z is in the language, then X, Y, Y, Z is in the language. X, Y, 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 Z is in the language. So I can pump this part as many times as I want and still get a string in the language. That is what the pumping lemma is about. Okay. Now, all regular languages have this property here. So all regular languages have this have a DFA. DFA as a number of states. And if you can find a string which has which is longer than the number of states of the DFA, that means that the DFA is looping. So that means that there must be a part on this string which can be pumped as many times as you want. This is true for all regular languages. So that if you find a regular languages, if you find a language and you find a string which is very, very long, and you show that this string doesn't have any part that can be pumped, okay, that means that your language is non-regular. Actually, it's much better if I actually show you the examples and show you what this means, okay? So let's say that we have the language of W, so the language of strings which are palindromes, and the central symbol of the palindrome is a hash. Okay, so as an example of a string in this language will be A, B, B, hash, B, B, A. Okay, so that if you read this from left to right is the same as if you read it from right to left. This is a palindrome. And specifically, this language here says that there must be a hash in the center and the other symbols must be A's and B's. Okay, so this is what this is about. So, okay, let's try and see if this language is regular. So if we find out that this language doesn't have the pumping property, then we can conclude it's not regular. Okay, so let's assume it is. Let's assume it has the pumping property. Okay, so let's assume it is regular. So let's assume L is regular. Is regular. Why we do that? Well, we're assuming something, right? And we see what comes out of this assumption. And if we reach a contradiction there, that must be that must mean that our assumption was incorrect. Okay. So if L is regular, there must be a DFA recognizing it. And if there's a DFA, this DFA has to have a number of states, right? Let's call it P. Now, for each string which is longer than P in the language, if the language has these strings, for each string, you know that W can be decomposed in X, Y, Z, so that strings of the form xy to the iz are still in the language, meaning that you can pump this y as many times as you want and still get a string in the language. We know that, we saw that before. So what you want to do to prove that L is not regular is to show an example of a string which is longer than P, which cannot be decomposed in any way. So there's no way you can decompose it so that you can pump apart as many times as you want. So this is your duty. You know, when you do the exercise, that's what you need to do. You need to find me a counterexample. So a W long enough, which cannot be decomposed. And then you can say, okay, then L must be non-regular. In this case, L2. So how do we go about it? Well, I'll show you how I do it. Well, in this case, my idea is to build a string which is made only of a's, hash in the middle, and then the same number of a's. Okay, so this is a palindrome because you have the same number of a's before and after. If you read it this way, it's the same as if you read it this way. And I want it to be longer than P. Okay, so what I do is I say that this number of so there's a P number of a's before and P number of a's after. So the length of the string is equal to 2P plus 1. Okay, so if L2 were regular, that must mean that I can find a way to divide it in 3 chunks, in 3 substrings, so that I can pump a substring as many times as I want. Now I'll show you that this is impossible with this string. And because it is impossible with this string, it means that there's no DFA that can recognize this string. So for any P, I can always, you know, I'm leaving possibilities open. I'm just saying that this string has P A's before, P A's after. So whatever P you throw at me, I can build a string with that P A's before and that P A's after. So it doesn't matter what number you throw at me, I can always find a counterexample. So I show you that it is impossible for this string. That means that for every P you throw at me, I can show you that there's no DFA that can recognize this string which is in the language. So that must mean that L2 is not regular. So our assumption was wrong. So how do I go about it? Well, okay, here I have 3 possibilities to pump, right? 3 possible, let's say, patterns of substrings which I can pump. So let's say I choose a substring from the left of the hash composed by some a's. It doesn't matter where I take it, so the important thing is that it contains only a's and it's on the left of the hash. But if I do that and I pump it, so I repeat this many times, as many as I want, and then I have the rest of the string. This means that I have many more a's before than after the hash. And that means that if I read this in this direction, it's different from when I read this in this direction. And of course, the hash is not central anymore. So this string is not in the language. So for any substring of a's on the left of the hash, I can choose I produce strings which are not in the language. So that's not a possibility. Let's do the opposite. Let's choose A's from the right side of the string. Well, I have the same problem. If I pump anything from here, if I pump some A's, I get more A's here than I get here, so it's not a palindrome anymore. Well, our last choice is to choose a substring which contains the hash symbol. So it doesn't matter how I choose it, okay? If I pump it, I get somehow a string which contains 2 hashes, right? Because I'm pumping it. Or even 3 hashes, 4 hashes. But my language only admits 1 hash in the middle. So that means that the string I'm producing is not in the language. So you see, for every choice of every substring I can choose from this string here, W, it's not possible to pump it. So it's not possible to pump any string in this W, any substring in this W, and get a string in the language. So that must mean that L2 is not regular. Okay, because for any P, I can build you a W that cannot be recognized by any DFA with P states, right? And that means that L2 is not regular. So let's do another example. Let's say we have the language of strings which have twice as many A's as B's, and particularly all the A's are before the B's. So an example would be AAB, for example, or AAAABB. So in this case I have 2 A's, 1 B. In this case I have 4 A's, 2 B's. So I have twice as many A's as B's, and the A's are before the B's. Now, is this language regular? No, it is not regular, and I can prove it to you. So let's assume that this language here is regular. Is regular. Then we know that there must be a pumping length P. So we're actually we're jumping a passage here. The fact that there must be a DFA, we don't care. The important thing about the pumping lemma is that you know there's a pumping length P, okay? Now, we know this P is the number of states in the DFA, but we don't care. The important thing is that this P is here. And actually, I would like you to... Yeah, it doesn't matter. So, if L3 is regular, you have a pumping length P, such that if you find a W, which length is more than P, in the language, you know for sure that W can be decomposed, W can be decomposed in X, Y, and Z, so that X, Y, I, Z is always a string in the language. So you can pump Y and still get strings in the language. Now, what I need to do, of course, again, is to show that for any P you can throw at me, I can find a W which is longer than P, but which it cannot be decomposed in this way, so that it doesn't, no DFA exists that can recognize this this string here, and then L3 is not regular. So how do I go about it? Well, let's see, I don't have much choice here. So the way my string is formed is quite constrained. So what I will do is just choose the string A to P, B, P, right? So I know this string here has length greater than P, okay? Because the length is actually 3P, right? You have 2P here and a P here, so it's 3P. You have 3P symbols. So for any P you throw at me, I can build a string like this. Now, this string looks like something like this. B, 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 B. Well, let's add more A's just for clarity. That's more A's than P's. Okay, so I have 3 choices, right? To pump a substring from this string here. So either I pump a substring of all a's, so it doesn't matter where, but I choose some substring which is composed only by a's and I pump it. But if I do that, I get something that is not in the language, right? Because if I add more a's, so let's say I add 1,000 of those, 1,000 of a's here, okay? I pump it, then I get many more a's than b's, but I don't want many more. I want 2 times as many a's as there are b's, right? So if I choose a substring of all a's, if I pump it, I'm not in the language anymore, because I'm not touching the b's, right? So if I choose a substring of only b's, again, if I pump this, then I get something that is different from here. So I don't have twice as many a's as b's. I get something else. So it's not in the language anymore. If it's something that is composed by a's and b's, well, again, if I pump it, I get something like this. Well, a b b, let's say a b b and b b, okay? But that means that there's this weird thing going on here, but my language wants all a's to be before the b's, but here I have this mixed thing, right? So this string is not in the language. So for any choice of substring from the w string, I cannot pump it, okay? And that's true for any p you throw at me. I can always find a string which is longer than p and in which you cannot find any substring to pump. So that must mean, again, that L3 is not regular.